Swayam Prabha. Digital India. Educated India.
It is a privilege to introduce Dr. Akshit Goyal, a faculty member at International Center for Theoretical Sciences. Dr. Goyal's research excellence has earned him recognition in the scientific community. He is a recipient of Associateship of Indian Academy of Sciences, an honor awarded to outstanding young scientists for a contribution to research. He has also received a research grant from the Department of Biotechnology for his work on climate resilient agriculture, focusing on sustainable and eco-friendly solutions. These achievements highlight both the quality and real-world impact of his work. We are truly honored to have him with us today. Please join me in warmly welcoming Dr. Akshit Goyal.
Hi, thanks. Okay, hi, morning everyone. Okay, you don't need to call me sir, you can just call me Akshit. But all right, so I am going to talk to you a little bit about some of the work that we do. And at first, it might sound a bit funny, but you know, over time we'll get used to this idea. But how many of you have heard of game theory? Okay, all right, and just to get a sense of all of you in the room, how all of you guys are doing science, right? Okay, how many people are studying biology? Okay, and okay, the people who are not studying biology, did you have a choice? What are you doing instead? Okay, so the choice is between computer science and biology. All right, okay, so the choice is between, and so anyone else has some other combination. So everyone's doing some combination, so and everyone's doing mathematics. Is that right? Okay, okay. Some people are not doing mathematics. That's fine. Okay, so and how many of you while doing biology have done computer science at the same time? Okay, all right. So because what I'm going to tell you about today is something that I was not very familiar with at all when I was in school, definitely also not when I was in college, which is that there's a lot of interesting science and a lot of interesting research work that you can do, which combines ideas both in biology and in mathematics and in computer science and in physics and in economics. Were people familiar with this? I was absolutely not. Okay, and so some of the work that I do in my group involves a combination of all of these. Okay, and so today what I'm going to tell you about is that we're going to talk a little bit about how we apply mathematical ideas from game theory in some aspects of biology problems. Okay, so if you don't know anything about game theory, that's also completely fine. I thought that we can just make it nice and simple by just starting off by playing a game. Okay, so we'll all just get together and play a game. And the game, you know, doesn't have a very nice title, but the title is very descriptive. It tells you exactly what the game is about. It's called Guess 2/3 of the Average game. Okay, anyone here played this game before? Okay, heard of this game before? Okay, good. So we're all playing a new game. So the game is exactly what it sounds like. So the rules of the game are as follows. You will get together in groups of 3. Okay, so find people around you. Go and find, you know, form little groups of 3. Introduce yourself, of course, if you haven't done so. And think carefully, privately. Don't tell anyone else in your group. Think of a number between 0 and 100. Okay, you can include 0, you can include 100. Okay, think of these numbers. Once everyone has thought of a number, simultaneously reveal your numbers to everyone in your group. So the 3 people reveal their numbers. And what do you think then you'll do, given the name of the game? You will compute the average and figure out what 2/3 of that is. Okay, and then the winner will be the person among the 3 of you who is closest to 2/3 of the average in your group. Okay, is it clear? Anyone unclear about the rules of the game? So you'll get together, look around you, find your neighbors or find someone else if they're close around. Form groups of 3. You can get up if you want. This is also an opportunity for you to stretch your legs a little bit. Think of a number. Once everyone's thought of a number, combine them, get 2/3 of the average, and then I'll take a little poll from each of the groups of what the winning number was. Okay? So we want the winner is the person who was closest to 2/3 of the average. I don't want 2/3 of the average. Okay? All right? Okay, you can go ahead and start. And also the adults in the room can also do this if they would like. Correct. Let me just clarify because there's some confusion about the rules of the game. So let's just take an example. Okay. So let's say the 3 of you pick 20, 30, and 40 as your numbers. Okay. Let's say A, B, C picks 20, 30, and 40. Okay. So what's the average of 20, 30, and 40? 30. What's 2/3 of the average? 20. And so who wins? A, B, or C? A. Okay. If A picked 22, A still wins. A picked 15, A still wins. Okay? Yeah. Okay. So clear? Those are the rules of the game. Okay, good. Let everyone finish. Okay. Are people converging on some winning numbers? Do people need some more time? Okay. If a group needs some more time, please raise your hand. Okay. It looks like every group has a winning number by now. So let's just take a quick poll. I'm just going to write down what the winning number. So I just want the winning numbers, okay? Not the 2/3. So in the 15 example, even though 2/3 was 20, I want 15. Okay? Okay. So, and I just want the numbers. I don't want to know which of you won. Yeah, okay. Okay, so let's just go around. Tell me, shout out some of your winning numbers. Okay, one at a time. 24. Okay. 25. Okay. Okay, maybe don't shout it out. Let's just go. Yeah. 37. Okay. 40. Okay. 45. Okay. 53. Okay. 7. Okay. 1. Okay. 23 and 26 is what I heard. 56, not 26. Okay. Sorry. 67. Okay. Very interesting. Okay. Did anyone get a number larger than 67? Okay, good. There's sometimes I've played this game where people had numbers larger than 67. Okay. Are we missing any groups winning numbers? 24? Okay. 10? Did someone say 10? Okay, I think I heard 10. Okay, are we still missing any groups numbers? Okay, we got everyone. Okay, excellent. All right. So, I mean, if you haven't heard of this game before, you can see like lots of people have played it online. You can chart out basically, what are all the different numbers that people get. Do you see a pattern, by the way? Like, if you had to play this game again, what number would you choose? Lower number, yes. I mean, lower than what? Like, which of these numbers would you pick if you were to play the game again? 40, okay. Okay, so this is sort of one of those interesting games which has a clear solution. If you think about it mathematically, there's a clear answer. But then somehow, for some reason, if you actually play this game again and again and again with people, you never you find that the answer actually almost never lets you win, except in one case here. So does someone, can we all now think mathematically or just rationally about what should the solution of this game be? What should be the right answer in some sense? So let's say that, let's say we do the worst thing possible. Let's say all three of you, let's say I am one of the players, I'm playing against two of you, right? And you both guess 100, right? Now I have to guess a number, right? What should I guess to win, right? The average of 100, 100 and whatever I'll choose, surely 2/3 of that will be 67 or less, right? So I should pick a number a little bit less than that, right? Because once I add my number, the average will go down, right? And then, okay, so once I do that, if you apply that logic, then people should pick that number, right? They should pick a number 67 or less, but then I should pick an even lower number because I want to be closer to 2/3 of the average. So what do you think, if I just keep doing this again and again, what do you think I should be picking? Why 30? Okay, so someone said 1, someone said 30. Let's hear, yeah, why do you think it should be 30? Yeah. Yeah. You will be closer, but now someone can pick 29 and beat you. Yeah, but so what are we imagining? We're imagining a situation where you're thinking from your perspective, right? Assuming what others are going to pick, right? Now, other people are not going to pick 100 if they are also playing this game, right? So what they are thinking, what you are thinking, they're also thinking. So they're thinking they should lower their number. So they're not picking 100 anymore. So you should think you should lower your number. So they should think they should lower their number. What's going to be the eventual outcome of this process? Why not 0? So actually in this case the solution turns out to be 0 because let's say each of you pick 0, then who wins? Everyone wins, right? So are you incentivized to change your answer if you're picking 0 and everyone else is picking 0? No, right? But for every other number, you are incentivized to change your answer, right? Is this clear? This is the first time you're thinking about this. This can be a little bit weird to think about. So if anyone's not clear about it, please ask me. Yeah. Yeah. Yeah, okay. So the question was, what if two people pick 100? I mean, so you're thinking from what you can do as a player, right? You're a player in this game. You're playing against other players in the game. Each of you is going to choose something to do, right? And what you choose to do will, you'll choose to do something that makes you win or increases your chances of winning. Yeah. So like the idea is that you don't know what the other person is picking, right? But you should pick something that, given what you don't know about what the other person is picking, maximizes your chances of winning until you have no incentive to change, right? So actually in that sense, 0 turns out to be the solution to this game, except we can see also at the same time that if you actually picked 0, in how many cases would you win? I imagine not a lot of them, right? Sure, 2 of them, right? So, I mean, this is sort of the funny thing about games that we have to keep in mind that, like, okay, of course, when humans are playing them, it's different from when you're thinking about it as a mathematical object. But this idea that you can think about things like games mathematically, where you can think about a situation where the solution to the game is a situation where none of the players have an incentive to switch. This was put forth by this guy over here, John Nash. Have people heard of John Nash before? Yeah. So he actually wrote this very brilliant like one-page paper. He obviously didn't call it Nash equilibrium at the time, but he came up with this idea that basically when you play games of this type, not just this game, but other games, and we'll play another game soon. In some sense, what you should do as a player is to arrive at a strategy, or what you pick in this game. For instance, the number that you pick was your strategy. In some other games, something else might be your strategy for what you do. And if you arrive at a set of strategies such that no one has an incentive to change, that in some sense is when the game seems to be, the game will, like, none of you will change your strategies anymore. You will reach a point where, everyone's doing the best that they can. And that point is what is called the Nash equilibrium. Okay? So this was a really important concept. So in the past game that we were playing, in this guess 2/3 of the average game, what was the Nash equilibrium? 0, right? In some sense. Okay, so here's another game that we can play, and it's called the stable marriage problem. How many people have heard of the stable marriage problem? Okay, so it's actually an interesting game. It's about 50 years old. It has many practical applications actually, which we'll talk about. But for now, let me just set up what the game is about. Okay, and the setup very simply is in terms of this very old Victorian setup. How many of you have read like Pride and Prejudice? Okay, some of you are familiar with it. If you are, then some of these characters might be familiar to you. But imagine a situation, this Victorian situation, where you have this ballroom and you have 4 men and 4 women. Okay, in general, mathematically, we'll think about n men and n women. But for now, let's just think about 4. Okay, so 4 men and 4 women. And what am I going to want to do? I want to do something with stable marriage, right? So what is it that we're going to try and do? We're going to think about matching them, right? We're going to think about matching the men and the women. How should we go about doing that? What's a nice way to do that? Sorry? Compatibility. Good. Okay, so we should think about compatibility. And of course, there are many notions of compatibility. This part is not a mathematically solved problem. But one way to make it mathematically tractable is the following. You can imagine a situation where each of the men and each of the women have ranked each other, have an internal ranking list of whom of the other type they would prefer. So just as an example, Elizabeth has her own list. She prefers Wickham the most, Darcy the second for some reason, Bingley the third, and Collins fourth. Okay? So, okay, same Jane has her own preference list, Lydia has her own preference list. All of the men have their own preference lists as well. Okay? This is just a random list that I have made up for this example, right? Okay? Okay, but this now allows us to talk about marriages and their stability, etc., etc. What should we do next? So we have do we have some notion of compatibility now, at least in this sense? What's the notion of compatibility? Preference, right? Preference is a notion of compatibility. And so what would everyone like? Everyone would like their first choice, right? Is that possible with this list? Okay, can you give me an example of why? Okay, good. So let's look at Jane and who? Jane and Bingley. Okay, so Jane prefers Bingley the most. Bingley prefers Jane the most. So they can be fine. Okay, so what's the problem? So if Jane prefers Bingley and Bingley prefers Jane, then Lydia and Bingley are not going to get, Lydia and Charlotte are not going to get their first choice, right? So clearly that's just one example, clearly showing that not everyone is going to get their first choice. So what should we do instead? What's a stable way to pair everyone together? Okay. Maybe let's do that again where people are saying one by one. Maybe someone here. Okay, there. Look for a situation where two people have the same first choices. Okay, so we found such a situation. Jane and Lydia have the same first choice. Okay, give us an example. Yeah, correct. Good. So they're paired off and happy. Okay, but in this game, what we need to do is we need to pair everyone up, right? Everyone in the end should be paired with someone else. Whoever doesn't get the first choice gets the second choice. Okay, that's a nice thought. Okay, the second choice are also yeah. Okay, so let's ask the following question. Okay, you guys are all thinking great. You guys are all thinking the right way. But all right, good. Let's think about the following situation. Let's say we matched all of them up somehow. Okay, let's say somehow I've said randomly, okay, Jane Bingley, Darcy Elizabeth, Lydia Collins, Charlotte Wickham. Let's say that's the pairing I've chosen. Okay, is like what should I look at? What should I look at as a solution to this? If I'm thinking about this as a game, what would be the solution? What would be the Nash equilibrium or the equivalent of the Nash equilibrium of this game? Everyone gets their highest preference possible. Good. And maybe slightly put a different way. How would I check that it's the highest preference possible?
You have a preference number, right? It's 1, 2, 3.
Good.
If you add them up, it's
Very
the
good.
lowest number possible.
Very good. Okay, so you're thinking about happiness, right? So you're thinking about I should find a situation where everyone is matched and everyone's least unhappy, right? Okay, that's something that we can definitely look at. There's probably going to be one such solution, right? Could there be many such solutions? Let me ask you this way. How would you go about finding such a situation? Let's say I wanted to maximize happiness the way that was just suggested. How do I go about finding it? I probably need some sort of algorithm, right? You guys are all thinking about some algorithm. Oh, let's find everyone's first choice. If that's not possible, let's move down to the second choice. So what we're trying to do is we're trying to write down some computer program in our heads, some sort of algorithm that will help us find one of the solutions to this game, right? Okay, someone else was trying to say something in the back. You can assign points.
First preference 5
Yeah.
4, 3, 2, 1.
Yeah.
For each of you, all of them.
Yeah.
Then we need to find the situation where the average of the points that the person gets, the match gets. The match will get a specific point. For example, Elizabeth and Collins. For Collins, Elizabeth will give you. For Elizabeth, Collins will be 1 point, and Collins, Elizabeth will be 3 points. So total 4. Like this, the one where all of them have the closest average will be the best.
Good, that's another guess for what you might want to do. And again, my question would be, how would you find, like now let's say you want to find the thing, like the matching that optimizes this quantity. How would you do that? You could do trial and error. That's a nice guess, right? Like that is the first thing that I would do, right? You just try and match things randomly and see what happens. Do you think that's likely to work? It's likely to be very inefficient, right? Like most of the times I randomly pair things up, probably will not work, right? So let me describe to you what the people who originally formulated this problem, the ideas that they had in their mind. Okay, and then we'll try to apply some of those ideas back to this problem. And in fact, we'll try to do some of this ourselves. Yeah, question. Yeah.
So we can give weights to each of the.
Yeah, good thought. Yeah. Okay, so we give weights to everyone.
We give weights to everyone.
Yeah.
Then based on that, we can find the probability, sir. With more weight having a better bias.
Good.
And then based on that probability, whichever gives the best one, we choose that.
Correct. Yeah. So you could define such a situation. You'll just have to search for many different pairings, right? By the way, how many different pairings are possible? So this is sort of one example pair. How many pairs are possible? 16. Why 16? Each person has 4. Right. But if the first person gets paired up with one of the 4, does second person still have 4 choices? 4 factorial, right? Which is 24, right? So there are 24 possible pairs that we have to search for. If there were n men and n women, how? N factorial. Does anyone know how n factorial goes as n? Does it go very fast or very slow, or very fast, right? So if you had 10 men and 10 women, and if you were just looking for every possible pairing, you'd have a pretty hard time, right? Exactly. Many 5 digits. What's 10 factorial? Anyway, it's something large.
We'll learn the rate of growth tomorrow in my lecture.
Okay, very good. All right. So let's say we do this exercise. We'll do some random pairing. Okay, some score-based metric we've decided. We'll give everyone some weights, etc. We'll try to minimize the unhappiness, maximize the happiness. What Goyal and Shapley, who originally came up with this problem, talked about a lot, and this is the context in which the Nash equilibrium comes up, was that they were very interested in the stability of any pairing. Okay, and by pairing I mean not just one pair, but a whole set of pairings. Okay, they have n pairs, and they were very interested in asking which of the n factorial pairs are going to be stable. Okay, and so what was their notion of stability? It was actually very similar to a notion of wanting to change something about what you're doing, which was that you should not have any what they call blocking pairs, okay, or eloping pairs. I'll just write down, because I didn't write it down on the slide. So we should have no blocking pairs. What is a blocking pair? Here's an example situation. So let's say here you have Collins and Elizabeth that got paired up, and Darcy and Lydia that got paired up. If there is a situation where one from here and one from here both prefer each other to their current partners, to the current person that they've been paired up with, they will run away. And so this will not be a stable matching. Okay? So the sense in which a matching is stable for this game or this problem for us are those configurations, are those sets of pairings which don't have any blocking pairs. Okay? No blocking pairs. And so somehow of the n factorial different pairings that we have, we need to find whichever one of them that satisfies this property of no blocking pairs. How do you think you'd go about finding such a pairing? Yeah.
We can go about pairing them at random.
Okay.
When you see that there is
Yeah, you can search brute force, right?
temporarily one person can be matched with another.
Yeah.
And he can go about, and if a better person, if he finds a
Very good. Good. Okay. So that's almost their Nobel Prize winning answer. Yeah.
So is the goal to create a case where everyone is happy relative to each other, or we find the best possible case?
So actually in this case we are not thinking about happiness so much at all. We are thinking only about this very local notion, this notion where whichever pairing you get should have this property that you cannot do better by finding someone else in another pair who will agree to also be with you over their current partner, right? So you might not be you might end up with a situation. In fact, we'll see a situation in a few examples in a few slides where actually you don't get your best. You actually sometimes get your worst possible choice in this game, but it's still stable because you cannot do any better given what all the other pairings are. Okay, and if this is confusing to you, we'll see very clearly some examples. Yeah, I can go back to the previous slide. Okay, now you're trying to really, okay, yes.
So what we can try is check if like two people have the same first choices, then they can get paired up.
Very good.
Check if who is getting like if they're part of the second choices. So here
Very good.
Bingley and Jane have each other as their first choices, so they will go.
Yeah.
Then if we see Elizabeth and Darcy both have
Can we try and listen to what all of our fellow students are saying? Yeah. Let's just go one at a time. Yeah. Yeah.
Then Elizabeth and Darcy, as well as Linda and Wickham, both of them have each other as the second choices.
Okay.
So that's there, which means Charlotte and Collins is the last one.
Good idea. Yeah. Okay. This is a like what Goyal and Shapley proposed was a little bit different, but a variation on this theme. Okay. So what was their solution? Their solution was something called I mean, at that time, this was the 60s. They called it a men proposing algorithm. But actually, in the interest of symmetry, it's perfectly symmetric. There's an equivalent women proposing algorithm. And actually, we'll play both of these algorithms together. Okay? So let me just describe to you what the men proposing algorithm is. In fact, once I start describing it to you, because you guys are so smart, you would already figure out what the situation is. Okay? And then we'll try to enact it here on stage. Okay, so I'll soon need some volunteers. But the men proposing algorithm is simple. First, all of the men will look at their first choices. So for instance, Bain will look at Jane, Darcy will look at Elizabeth, Collins Jane, and Wickham Lydia. Okay, and they'll all go and make a proposal. That's why it's called the men proposing algorithm. They'll go and make a proposal to their first choice. Okay. You can also imagine a women proposing algorithm where the women are the active side, right? Then what do you think will happen? So Bingley will go to Jane, Darcy will go to Elizabeth, Collins will go to Jane, Wickham will go to Lydia. All of the women that received one proposal only, what do? They accept it temporarily, correct? Yeah, they accept it. And there are some women who receive two proposals, right? So in this case, Jane would receive two proposals. What should she do? Choose whichever is better, right? And reject the other. Okay? Now that's one round or one iteration of the algorithm. At the end of this iteration, some of the men have found temporary partners. Some of them have not. Okay? So the ones who have found someone, they stay. The second iteration, focus only on the ones that that got their proposals rejected. Okay. So now all these men, what do they do now? They now go to their second choice. So for instance, in this case, what should have happened? Darcy and Elizabeth get engaged. Wickham and Lydia get engaged. And which of Bingley and Collins wins? Bingley wins. So Collins is left. Right? So Collins would now go to Elizabeth, and now now Elizabeth gets a second proposal. She's already with Darcy. So what should she do? She will look at her list, and who does she prefer more? Darcy. So she will stick with her, and then Collins will go about and she'd ask Lydia. Lydia is already paired up. What should Lydia do? And then Charlotte, and then Charlotte hasn't received any proposals. The minute every man and every woman are paired up, the algorithm stops, the game is over, and you are guaranteed mathematically to have a stable state. Okay? And there's actually a very simple and beautiful verbal proof for the fact that this should be stable. Maybe now you can come up with a proof of why this will be stable. Don't feel like you hear the word proof and now it's suddenly very complicated in maths. right? It's still the same logic that you guys were giving me. Why would this situation be stable? Maybe, yeah, you? Oh, okay. The question is, even if you start with the women, meaning if you do the women proposing algorithm. So, very good question. Excellent question. So, you could imagine doing all of this with the women proposing algorithm. The women go first, they propose to all the men on their top and keep going down. That will also result in a stable state. Okay? What is not guaranteed is that it's the same stable state. Right? So what I haven't told you yet and what we are arriving at now is the idea that there is not only one possible stable state always. There could be multiple of them, right? And in fact, there might be even, like let's say you arrive at one state using the men proposing algorithm, one state using the women proposing algorithm. Does that mean there are only two states? There could be even more. Right? And so one question that I wanted to think about, which we'll come to in a bit, is how do you find those other ones? Okay? There's also an algorithm for that. Okay? So before we get to the proof, I want you to keep thinking about how you'll prove this statement that this algorithm will give you a stable state, is guaranteed to give you a stable state. Let's play this game together so that we get a little bit more of a sense of what it's doing. Okay? So for this game, I need I need 6 volunteers. I need 3 from the women here, and I need 3 of the men here. So can I have 3 volunteers from each side, please?
What are we supposed to do?
Yeah, we are going to. Yeah. So what? Excellent question. So I have here some very scrappily put together sheets with 6 names. And in the next slide, I actually have a set of preference lists that we all are going to have available for us to look at. Very unimaginatively, the names are A, B, C, J, K, L. So Anna, Beth, Claire, John, Ken, Larry, to make it simple for us. And what we're going to do is that we're going to try and act out the men proposing algorithm in person. Okay? No one has to do an actual proposal. Yeah. We're just going to try and do all these moving parts that we just talked about out so that we can see it very clearly, right? Otherwise, I was saying, look at this list, look at that list, that gets confusing. So now that people know what you're supposed to do, can we? Okay, great. All right, so all I want you to do is just to put up, just put up and hold up your names so that everyone can see them. We can also have you stand in order. So there's Anna, Beth, and Claire, and maybe you can stand in this. Can everyone see the? We should all be able to see the preference lists. Okay. Can everyone has access to the preference list and everyone can see them? Okay. So we have Anna, Beth, and Claire here, and we have John, Ken, and Larry here. Okay. And the preference lists are all in the back. Okay, for everyone to see, including you guys. So you guys should remember your preference lists. Okay, and so we're just going to work out the men proposing algorithm first. Okay, all right. So what should we do first? So all of the men should go and make proposals to the women on the top of their list, right? So what should those proposals be? So for John goes to Beth. Okay. Ken goes to Beth. And Larry goes to Claire. Okay. Could we please have the... Okay, yeah. So maybe we can have the women stand here in the center, because in the first version you're going to be passive, in the second version you're going to be active. Okay. Okay, so all right, go ahead. You should just go, go to the, each of you go to the women on the top of their lists. And hand over your papers as... Okay, so Beth got 2 proposals, Claire got 1. Anna unfortunately didn't get a proposal in this round. But that's fine. Okay, so what should happen now? Okay, Claire, of course, it's very simple for her, right? Claire says yes to Larry, and you guys get paired up for now. Okay, what will Beth do? Beth should choose John, right? And so she chooses John. So John go with Beth and hands back Ken's proposal. Okay, now Ken is left. What should Ken do? Maybe let's just make sure that people are all like, yeah, okay. Okay, so now Ken does what? Ken goes to Claire, right? Okay, so if Ken goes to Claire, what does Claire do? Claire will choose Ken, and the temporary engagement that her and Larry had gone. Okay, that's fine. So now, who do we have left? Is everyone paired up? No, right? Anna's not paired up and Larry is not paired up. So what does Larry goes to Anna? Anna accepts. Sorry, Larry goes to Beth, right? Okay, so Larry goes to Beth. Beth says no. So Ben prefers Larry the most. Okay. Relax. Okay, relax. Okay, let's try to do this again. Maybe the people who are unmatched go to the left, and the people who are matched right now go to the right, so that we can see very clearly. Wait, I thought Larry lost out, no? Larry won again. Okay. Okay, who is matched with who, right? Okay, so Larry went to Beth. Beth said yes, and who was Beth with earlier? John. Okay, so now John is left. So now what should John do? John goes to his second choice, which is Anna. Anna says yes. That's the only proposal she received. And now we're done, right? Is everyone paired with every... Yeah. Somehow people don't want to pair up, but that's fine. At this point, everyone is paired up with everyone else, and the algorithm stops, right? And the claim is that it's a stable marriage. Okay? So can someone prove... Can someone give a nice verbal argument to prove that this is stable? So remember, men were always trying to go down their preference list, right? So if it so happened that all the men in their first set of proposals managed to find someone, then of course they got the best deal they ever could, right? Can we try and have one conversation? Yeah. So if in the case that all of the men happen to get their first choice, then it would obviously be stable, right? Why? Because then none of the men want to change, right? In this case, that is far from what happened, right? This is a situation we designed specifically so that we can see a lot of the things of this type. But in this case, it was still true that men are always going down their list, right? And the only reason they go down the list is when they get rejected by another woman, right? So that means automatically again that none of the women who they're not with and they prefer more, they've already been rejected by them, right? So they could never hope to do better than what they currently have, right? And so this is a very simple proof of seeing why this marriage should be stable, right? You can see one more property of the stable state or the stable marriage that we get as a result of doing the men proposing algorithm. Can someone see what that is? Who here got the better deal? The women on average or the men on average?
I feel like both. Because like both
Yeah.
like two of the couples here. Sorry, no, but I mean, like, two of the
Yeah.
people here.
Yeah.
They got their first options.
Yeah.
And the remaining people.
No, I thought that a bunch of people.
John got the second option and
Yeah.
so did Anna. So John and Anna, they have the same preference.
Yeah.
Beth got Larry.
Okay, someone here has something to say.
Average same for both.
Yeah, okay. Yeah. Okay, good. Yeah, so you have something to say. Yeah.
So the only reason it's
Yeah.
stable is because the top men who had the best preferences, equivalent to the women's preferences, they got their preferences. So then the other men who it's impossible for them to beat their other pairs, they went down the list to get the most stability. So then, even though like the worst case here, it is not the most stable, it is the only possible case for the worst case.
Yeah, meaning the cases here are stable, right? It's stable in the sense that we define. It's stable in the sense that no one has an incentive to switch, right? Okay, let's actually try to do the same thing in reverse. Let's now try to play the women proposing algorithm. Okay, for the same set of lists. Okay, so maybe the men can stand in the center now. And yeah, everyone make sure you have the right placards.
They'll both result in different stable pairs. So then which will be better?
We'll see. We'll see. So everyone remembers what pairing we got when we did the men proposing algorithm. Let's just write it down so that we don't forget. So what's the
John, Anna,
okay? So let's write it down.
Larry,
John, Anna.
Beth, Larry.
Okay, and everyone else should check if this is right.
Anna.
Oh God. So these are the men. This was what? Beth. And this is Ken and Claire. Okay. All right. So now we'll do the women proposing algorithm and see what we'll get. So this is men proposing. All right. Okay. So what do you think will happen now? So the women all go to the top of their preference list. So Anna goes to Ken, Beth goes to Larry, and Claire goes to Ken. All right. Go ahead.
Hand over your sheet.
Yeah. Okay, so poor John is left behind for now, but Ken got 2 proposals. So what should Ken do? Ken can't choose Beth because Ken didn't get a proposal from Beth, right? So Claire. So Ken chooses Claire and Anna is left over, right? So now Anna, okay, which of you is Anna? So Anna goes to John. John got a proposal. He didn't have a proposal before, right? And is it over? Everyone got paired up, right? Oh, sorry. Okay, so now let's write down. Let's just make sure that.
No, please no.
So what did we get when the women proposed? Same, right? So you got the same stable pairing, right? None of them is much better than the other, right? And like many of you pointed out, everyone got kind of an average deal, right? Some of them got their first choice, etc., etc. Some of them didn't get their first choice. Is this always going to be the case? Okay.
only 3 people, like if we raise the case to n people, then from the men proposing algorithm and women proposing algorithm also the same status.
No, so this turns out to strictly speaking be not true, and the reason is it all depends on these lists. Even if you have more people, it depends on how the lists are arranged, right? So you can also see that the way that the thanks a lot. Let's just give a round of applause to everyone. You can go back to your seats. Yeah. Okay, so what you can see is that the lists really matter, right? Because they are the ones that determine who does what in 1 round or 2 rounds and so on and so forth. Right, so here's another example of a slightly different shuffled versions of the lists. This time we won't try and do everything on the stage, but let's, by now everyone has a hang of this problem. So like, now do you think the men proposing and women proposing algorithms will give you the same answer? Maybe try and work it out in your notebooks, and then we'll try and write down what the solutions are to each of them. By now all of you know the algorithms really well, so maybe I'll give you a minute or two to work out both solutions, right? Okay, should we try and start writing down the answers? Okay, maybe we'll do the men proposing algorithm answers from this side, and then this side stay quiet during that time, and then when we'll do the women proposing algorithm, we'll do it from this side. Okay? Okay, so what's the solution to the men proposing algorithm? Anna and what? Anna goes with Larry. Okay. Beth goes with John. Claire goes with Ken. Okay, does everyone agree? Anyone has any objection? Okay, good. Let's talk about the women proposing algorithm. What do you get from this? Anna goes with Ken. So it's already different, right? Beth goes with Claire goes with John. Does everyone agree? Anyone has found a different answer? Okay. Are these two states the same? No. Are they both stable? Okay, let's have a quick vote. How many people think yes, it's stable? Okay, roughly half the class. And how many people think it's unstable? Okay, which of them is unstable? So remember, the notion of stability is not whether you got your first choice or not, right? What's the notion of stability? If you got a bad choice, can you go and get a better choice and convince that person that you are the better choice for them compared to their current partner? Is that the case? If after men proposal, women proposal happens, what do you? Yeah. Yeah, so that's why we have the women proposing algorithm, right? So okay, so here's what I want to say.
How do you tell which answer is better between these two?
There is, right now we are not talking about which answer is better at all. It's a good thing that you're asking about which answer is better, but we are right now just asking about all the different situations that are stable, right? Stable is stable, okay? Once you have multiple stable states, you could ask yourself which one is better or which one is worse, right? Right now we're only probing and asking which ones are the stable states. So are both of these stable? Yes. Okay, good. And you can try and verify. Come to me during the break if you're not clear about this. Yes.
Like if we match everybody up with their second choice instead.
Yeah.
Isn't that more stable than one person, like all the women ending
Yeah.
up with their first choice and then?
There is no notion of more stable and less stable. Okay? there is only a notion in how we've defined it as to stable or unstable. It's a binary choice. Okay? So, but you're all thinking about a good set of things like, okay, we don't just maybe care about the stable states, we might also care about which ones are a little bit more stable, which ones are a little bit less stable. But right now we're only asking about absolute notion of stability, which is just, do they have any blocking pairs or not? Okay, which neither of these have. Okay, so in this case, so how many states? So we found 2 at least, right? Do you think that there are more? So by the way, how many states are there here total? 6, right? Why 6? 3 factorial. So 2 out of 6 we have found. Someone thinks it's 3 or 4. Okay, so how do you know? So let's just first make sure we knew these ones. So we did the men proposing algorithm. When I did this yesterday, I got John with Beth, Ken with Claire, and Anna with Larry. That is indeed what we wrote here. And you can see what I also wrote down here nicely for us is that you can see all of the men got their first choice. All of the women got their third choice. That's because of a consequence of how I made this, right? When we did the women proposing algorithm, let's check again. John goes with Claire, Ken goes with Anna, and Larry goes with Beth. Yeah, that is indeed matching what you guys found. And now you can see all of the men found their third choice, got their third choice. All of the women got their top choice, right? You could surely imagine, like someone was saying, you could imagine a situation where there was a mixture of the two, right? How would you go about, let's say you wanted that, how would you go about finding those other stable states? Yeah, so what I heard were 2 things. One was do random pairing, which indeed you can always do random pairing with 6 pairs. It's not a problem. The other thing was look at the second choice. And there's a sharper way of saying look at the second choice, which is that usually what you do is that you create temporary breakups or temporary divorces. Okay, so one thing that you can do is you can start from any of these states, okay, create a temporary breakup. Let's say you can say that Beth says no, okay, temporarily. If you do that, then of course, then John cannot go with Beth, then has to go down to the second woman in his list. And this will trigger a whole cascade of new proposals and new acceptances, etc., etc. And that may also stop at some point where all the men and women have received proposals. That is also guaranteed to be a stable state. So there's a separate proof, there's a separate algorithm. This algorithm is called the break marriage algorithm for obvious reasons. And this algorithm also you can prove mathematically gives you stable states. And in fact, now you have a general recipe of finding all the stable states. Start off with the men proposing algorithm, temporarily break up one of the marriages, go down until you find a new marriage. Then you go back to the men proposing algorithm, temporarily break up another marriage, etc., etc., etc. Okay, and there's also another mathematical proof which I won't have time to get into, which is that if you do this enough number of times, you will end up with the women proposing algorithm. So all of the stable states lie along a nice hierarchy from men proposing to women proposing algorithm. And you can see that hierarchy is clear. In the men proposing algorithm, men get the best deal. The women proposing algorithm, the women get the best deal. And everywhere in between, so here's what you would get, for instance, if you break up the men proposing algorithm, you can see that everyone got their second choice, which indeed was what one of you said. Right? So in this case, it's designed in a way that everyone getting the second choice is also stable. Right? In the more complicated cases, it might not be this. Someone might get the second choice, someone might get the third choice, and so on and so forth. Okay? And because of this proof that all the stable states lie between the men proposing algorithm and the women proposing algorithm, what can you now say about this first exercise that we were doing? So here, how many stable states do we expect to have? Not states, stable states. Okay, someone says 1, someone says 3. Okay, why 3? This is the first one that we did out on stage. Exactly. So there we found that men and women proposing were the same. So indeed, only one stable state. You can go there, you can go here and verify later if you want, that now if you do this break marriage algorithm, you will actually come back to the same state at which you started. Okay? Fun? Alright, so that's what I'll say about the stable marriage problem for now. What we'll do now is that we'll take a little bit of a break. What I haven't told you is how any of this has anything to do with biology, right? So I'll do that in the next lecture.